Okay, we are ready to look at kinetics again. We looked at kinetics for chemical reactions. Now let's look at it for nuclear reactions. Kinetics means the speed at which the reactions take place. And so we're going to see that it follows first order kinetics, just like first order kinetics when we were in our chemical kinetics chapter. If you look at the left-hand side, you'll see the notation that we were familiar with for first order kinetics. The rate is equal to K times A raised to the first power, right? So we see that we have our first order rate law, and in a similar way, if you were talking about rate of decay, it would have a similar equation. They just use different symbols. The symbol for the constant is a lambda, okay? And this would be the number of nuclei. That number of nuclei could be actual number, 5 billion. It could be a mass. It could be in terms of moles. Doesn't matter in terms of what unit it is in. So that is the first thing that we see. Down at the bottom, we see the half-life equation. They look very, very similar. It is the natural log of 2, which is 0.693, divided by its rate constant. We use a K when it was chemical kinetics. We use the lambda here. What is missing in the middle there is our integrated rate law. And as a reminder what it looked like in our kinetics chapter that we've seen before, it's the natural log of A concentration over the initial concentration, which is equal to minus K times time. That was the integrated rate law for our first order kinetics. Since nuclear decay is first order, we have a very similar equation. It just looks different because of the symbolism that we use. The number of nuclei at some point in time divided by the initial number of nuclei, which is equal to minus the constant, which is not K but lambda, times your time. So it has a very similar, straightforward look to it. So we are going to just be reviewing now first order kinetics in this chapter, and let's look at working through this problem. I will turn to the light board here and we will walk through this problem together. So I read the problem and I see that time is given to me, okay? I see that I'm trying to determine the half-life. Pause and read through the whole thing and see what kind of information is provided for you there. Now what I know is if I'm trying to determine the half-life, that if it's first order kinetics, that we can determine the half-life if I know the constant. Okay, now you can use symbols of K still. It doesn't matter to me. You don't have to change the symbolism. I will keep the symbols different because in nuclear chemistry, this is what they use. So I need to know the rate constant, okay, lambda. I look through the problem and say, did they give me the rate constant? And as I look through there, no, they did not give me the rate constant, okay? And I do want to back up and mention one thing. In this problem, it says to calculate the half-life. It is not telling me what to calculate the half-life in units of. I'm going to choose to do it in days, okay? That will be my choice there. Since they didn't tell me, days will come out naturally for me. All right, so that's the first thing. We know that we are going to do the half-life, so we need that equation. If we have that equation, if we had the constant, we could get the half-life. All right, so what did they give me? Well, they gave me a time it started and a time it finished, so I could figure out how long it took. It told me a rate of how fast it was initially and a rate of how fast it was at some time in the future. And so I'm going to choose to use this equation to get my constant. It's the only other one that I've got. It would be the number of nuclei at some point in time divided where I started, which is equal to minus the constant times time. Okay, so it's got the constant in there I need. The problem is, it did not give me the disintegrations. It didn't give me amount. It gave me rates, rate of disintegration. How many disintegrated per time? Well, here is what I know. I know that for first order kinetics, this is true. I know that the number of nuclei and the rate are proportional. So if they are proportional, I don't have to work with the number of nuclei. I can replace the n with rate, okay? So if they're proportional, I can do this ratio in terms of rate instead. So that is going to give me the natural log of the rate at some point in time down the line, I'll call it time t, okay, divided by the rate initially is equal to a minus this times time. So that's the equation that I'm going to use. I was given these two things. I'm trying to solve for this one, so I better have been given time. So I go back into the problem and I'm looking for time. Well, it started to get my time. Okay, this ran from December what? December 3rd to December 17th. Okay, that is 14 days. Now, a little secret, you'd get the same answer if you just said, that's 14 days, close enough. But I'm going to go ahead and see how much additional I have, because if you notice there on December 3rd, it says on December 3rd it started at 2:15. No, it didn't. It started at 1 o'clock in the afternoon, and it went to 2:15 on that other day. So that is an additional, besides the 14 days, it is an additional 1 hour and 15 minutes. Okay, now how can I turn that into days? Well, 1 hour and 15 minutes is 75 minutes. So I can say, I really don't want minutes. I want hours. There are 60 minutes in an hour. And I really don't want hours. I want days. And there are 24 hours in a day. So this additional few minutes that I have right here turns out to be 0.052, that's a 5, days. Okay, so that is how much time I have. I have 14.052 days. So now I'm ready to go and figure out the rate constant, okay, lambda, using this equation, plugging everything in. So the natural log of the disintegrations at some time in the future, which was your December 17 day, is 2.6 times 10 to the 4th disintegrations per minute. That's a rate, okay? And at the initial time, if you look back at the problem that's given to you, it tells you that at some point in the, or at the initial time, that's what we put down at the bottom, it's 9.8 times 10 to the 5th disintegrations per minute. So it's slowing down. It started out faster. It is going to slow down, so it makes sense that that's a smaller number. And that is equal to what I'm trying to find, the constant, times my time. And my time was 14.052 days. 14.052 days. So now I'm going to solve for my lambda. Now I'm going to talk you through what I did, and you just listen to this and see if it makes sense to you algebraically. I'm going to first divide these two numbers and then take the natural log. And then I'm going to divide by 14.052 days. That is going to leave me with my lambda. Okay? Divide, that cancels these units out. Okay? That part is unitless. I'm dividing by 14.052 days, and that's going to give me 0.059. Nope, it's not going to give me that. I'm looking at some other number there. Let's erase with my fingers, and let's go 259. I don't know where I got that O. What would be the units? Well, you're dividing by days, so it's days to the minus 1, or 1 over days. So now I know the constant. It is 1 over time as a unit, which we expect for first order kinetics. All right, we got it equals. Are we answering the question yet? No, because it's asking for the half-life. So what is the half-life? The half-life is equal to 0.693, which is your natural log of 2, divided by this number, 0.259 days to the minus 1. That is going to give you 2.7 days. Well, you can't see that D. I'm going to just put it under here. That is a D right there. 2.7 days. So the half-life of this reaction, based upon the information given, is just 2.7 days. In that much time, half of it will have gone away. All right, so that is how we work through a first-order kinetics problem in the world of nuclear chemistry, and it is no different whatsoever than what we did back in the chapter on kinetics. Now, what would you use this for? Okay, why be able to do these kind of calculations? Well, there's lots of reasons to do it, but one of them that I want to mention is you can date objects by knowing their half-life, okay? Going in and making a measurement of how much is there now versus how much you know should have been present initially, and from that you can determine how old an object is. Radiocarbon dating is wonderful for this because we know that living organisms bring in carbon, inhaling and exhaling and eating and you know what you do after you eat. All of that's happening and keeping a very constant amount of a radioactive carbon isotope in our body. But as soon as a living organism dies, then that decay series, you're not getting that replenishment that's happening, will start off happening, and you can know based upon how much of that radioactive isotope of carbon is in there, you know how old the object is. So I'm not going to go anything more in my discussion with you, but you should read about radiocarbon dating in your textbook, becoming familiar with the process of how to date an object that used to be living based upon this method.